Calculating the solubility of an ionic compound when a common ion is present. Okay, so what we need to do first of all is work out which one is our sparingly soluble compound and which one is our soluble compound. So calculate the solubility of zinc 2 hydroxide in pure water. So that implies that is our sparingly soluble compound, and in a 0.006 molar zinc sulfate solution. So that implies that that is going to completely dissolve. So we need to look up our KSP for our zinc 2 hydroxide, and that shakes out to be 3 times 10 to the power of minus 17. So very much sparingly soluble. Okay, so we can write our KSP expression. First of all, I should say we should write an expression for the dissolution of our zinc hydroxide. So that is going to dissolve sparingly to the zinc 2 plus cation and 2 hydroxide anions. So do be aware of stoichiometry in this case. Let's make you look tidier. Take you over here. Okay, so now we can write a KSP expression and we know what that should be equal to. So KSP is going to be the concentration of zinc 2 plus times the concentration of hydroxide, and that will be squared. So for pure water, first of all, that is relatively straightforward. We've been asked for solubility in grams per mole, so we're going to have to convert solubility from moles per liter, molar solubility, into solubility in grams per liter. So we do need to know the molar mass of our sparingly soluble compound, which is our zinc hydroxide, and that is typey, about 99.39 grams per mole. So every 1 mole of zinc hydroxide weighs 99.39 grams. All right, so that'll do. So I can then go ahead and type for just in pure water. We can do an ice table. So my monitoring of the concentration of zinc 2 plus, my concentration of my hydroxide. So we don't have any common ions, so my initial concentration of zinc 2 is 0 and hydroxide is 0. The change then, for every 1 mole of zinc hydroxide that is dissolved, that is going to yield plus X moles of zinc ions and plus 2x moles of hydroxide ions, because there's 2 hydroxides per zinc hydroxide. So at equilibrium, in terms of X, that's going to be X and 2x. I can substitute those into my KSP expression. So KSP is going to be X times 2x, and that will be squared equals KSP. So 2x times 2x is going to be 4x squared. So that's going to be x times 4x squared is just going to be 4x cubed, right? So now I can rearrange and solve for x, because we know KSP, right? So x is going to be the cube root of KSP over 4. Bear with me a second while I try and make this look pretty. And that'll be the cubic root, so I'm going to have to try and do a little 3. Or you can just do it to the power of a third. That worked out okay. And of course, KSP, we can look it up. That is 3 times 10 to the power of minus 17. So that gives me a value of x of 1.945. That'll do, times 10 to the power of minus 4. And that is in moles per liter. If I want to convert moles per liter to grams per liter to get it from molar solubility to solubility, I'm going to use my molar mass. So every 1 mole of zinc hydroxide, so I had to think about that for a second. Zinc hydroxide weighs exactly 99.39 grams. So we can see that moles will cancel out, and that will give me units of grams per liter, which is solubility. Cha-ching. And that shakes out to be hang on a second. Yeah, I mess up there. I can't read my own writing. Um, so that x turns out to be, I really scrawled this, 1.957 times 10 to the power of minus 6. It's always good to have clear workings, right? Moles per liter. Um, and then, whoopsie, convert that to grams per liter. So 99.39 grams is the mass of 1 mil of zinc hydroxide. So then that will shake out to be, as the moles cancel out grams per liter. Now I get, skipping ahead, 1.945 times 10 to the power minus 4 grams per liter. Okay, and we were asked for two significant digits, so honestly I can just write 1.95 times 10 to the minus 4 grams per liter. Not even two significant digits, not two decimal places. Good lord. That'd be 1.94 something, wasn't it? It'll be 1.9. Let me just fix that by going it. All right, so what if we have zinc sulfate solution? So the complicating factor is then if we have a zinc sulfate solution, sulfates are usually soluble. So what happens then is that's going to completely break apart into ions. So the ions we'll see is zinc 2 plus and the sulfate anion. And one of these is a common ion. In this case, it's going to be the zinc, right? So we start with a non-zero concentration of zinc. In this case, we can see that there's a 1-to-1 mole ratio. So in the same volume, let's just pretend it's a liter of water or whatever. Per liter of water, we have 0.0060 moles of zinc sulfate dissolving, which is going to yield us the same number of moles of zinc 2 ions, right? So 0.0060 moles of zinc 2. It's a 1-to-1 stoichiometry in this case. So our concentration of zinc 2 plus, our common ion, is not starting at 0, it's starting at 0.0060 molarity. So do be careful with stoichiometry on these kind of questions, right? If it yielded 2 moles of zinc ions for every 1 mole of compound that dissolves, you'd have to adjust that starting concentration. So now if we are in the zinc sulfate solution, we just have to adjust our ice table very slightly, that being that the initial concentration of zinc is now non-zero. But we are going to go ahead and do the extra small approximation, so the math isn't going to be as hard as you think. Why can we do the extra small approximation? Well, because we know the presence of that common ion is going to inhibit the solution of the zinc sulfate. It's like a kind of concentration stress, right? We are causing there to be an excess of these zinc 2 ions on the right-hand side of the equation. So according to Le Chatelier's principle, that is going to push the equilibrium to the left, further suppressing the dissolution of our sparingly soluble compound. Okay, so the change then is going to be the same, plus x and plus 2x. My equilibrium is also going to be the same, x and 2x. No, it's not, because I start with 0.0060 plus x. Of course I do. That's talking for you. So we're going to substitute those values into the KSP expression. So KSP, where have we gone? So KSP is going to equal the concentration of zinc 2 plus at equilibrium, which is going to be 0.0060 plus x, and then times 2x, and that will be squared, coming from the KSP expression. So what we can do is we can use the x is small approximation to just ignore that plus x, because that really is going to be very small if we are if we have a common ion which is going to prohibit the further dissolution of the zinc oxide. So we're using our chemical knowledge there. So I can simplify that to KSP equals 0.006 times 2x squared. So then we can just rearrange and solve for 2x. So we should end up with x, come here, x equals the root of KSP over 0.006 times 2 Where is that gone? So I'm going to have to draw my little square root here, and we know KSP is equal to, sorry, not a square root, cube root, right? 2x squared times, no, it's square root. What are you doing, Aaron? More caffeine required, so we don't have to do anything special there. So we can just substitute in that KSP is 3 times 10 to the power minus 17, and we will end up with X, which is our solubility, our molar solubility, equals 3.536 times 10 to the power minus 8, and that is in moles per liter. Okay, so that is our molar solubility of our zinc hydroxide, which will be the same as the molar solubility of our zinc ions. So we can then convert that into solubility in grams per liter by using the molar mass of the zinc hydroxide as a conversion factor. So 5.536 times 10 to the power of minus 8 moles per liter. And I know that 1 mole of my zinc hydroxide is going to weigh exactly 99.39 grams, because that is its molar mass. So moles is going to cancel out, give me units of grams per litre, which is totally appropriate for solubility in grams per litre. And that comes out to be 3.514 times 10 to the power minus 6 grams per litre. So if we compare the general, order of magnitude between a pure substance, pure water, that's 10 to the minus 4 for the solubility, and with the common ion, 10 to the minus 6. So the solubility is decreased by a factor of 2 orders of magnitude by the presence of that common zinc cation. So we were quite right to assume that we could do the extra small approximation.